Were we live? Oh my word. So here's the thing, I don't know if I've been live or not. Ah, I'm live now. Hi everyone. Hi everyone. That was actually quite good. That was actually quite good because we did a practice. We did a practice introduction. Hi everyone. My name is Zako Siema and I'm an embedded firmware developer. Today we're going to be working on a CPU I've been working on for a bit over a year. Well, I haven't. The last time I worked on it was a few months ago. I haven't worked on it in a bit, but it's been a while, and these things take a while. So what I want to do today is to probably um, go through the code that I've written, which lives on this one here. It lives on this. It lives on this repo. You can get it from this repo. You can see that here. You can see that at the top, which is here. As it lives on that repo. And what I would really want to do is go through the code that I've written. There's a Verilog module. Sorry. There's a Verilog module that implements a CPU, and what I would like to do is basically make sure that all of the instructions that I've implemented are actually the ones that are supposed to be done, and basically make sure that it's at a state where we can start working on it again, because I can see what the Verilog is doing, but I don't remember what in the RISC-V world I was doing, and I don't remember if I was actually interpreting it right or wrong. Please, if you're around, please leave a comment so that we can see if the new comment system actually shows your comment on screen, and that would be really awesome. Yeah, so that's what we're going to be doing. We're going to be reviewing this Verilog code, see if it's actually implementing the CPU as we wanted it to implement the CPU, explain and answer any questions that we get during the session, and then we'll see where that goes. We'll see where that goes, and we can learn together and make sure that everything goes together. So the aim here is to get the thing working or broken at a known state, and then I don't know how often I'll keep streaming. I will probably try and do it every other day or every day. When I get into a rhythm, I can do them every day, and sometimes I can even do them multiple times a day. It's just that it's been a month off, and now we're getting back to this after a very taxing month at the day job, which is still going on and it's still going to be taxing, so might as well now get back to this. So yeah, welcome everyone. If anyone has any questions at the moment, please let me know, and then we can get started. Yeah, so what we're working on today is Verilog, and Verilog is how do I explain this? Verilog is a flavor of register transfer level language. So a register transfer level language is basically RTL. It's a hardware definition language. I'm going through acronyms like really. So Verilog is an RTL. And what is the meaning of RTL? RTL computing, register transfer level computing. So what is RTL? Register transfer level, which this is something you do in digital circuit design. Register transfer level is a design abstraction which models synchronous digital circuits in terms of flow, data, digital signals, data between hardware registers, and the logical operation performed on those. So this is how you code FPGAs. And when you write code on FPGAs, you basically build digital circuits that you can use to do whatever. So, and one of the most popular digital circuits, one that pretty comes to mind quite easily, is a CPU. And it's I think it's a complicated one to build. I don't think it's a very easy one to build, but it's quite, it's more straightforward than the other things. You can make other things that are quite straightforward. You can make hardware blocks. You can make peripherals, things like I2C, things like UART, things like USB, things like CSI, DSI. You can make hardware peripherals like that, but those ones also still already need some sort of master to use them, and this master is going to be something like a CPU. So sometimes it makes more sense to start with a CPU, and then you can make all of these pipelines later down the line, and you can cobble them up together. So what we're going to do today is we're going to look at this CPU that I built, that I started working on last year. And this CPU is modeled on the RISC-V architecture. RISC-V is RISC-V or RISC whatever, however you say it. RISC-V is a free and open source standard instruction set. It's a reduced instruction set, so which means it is not a complex instruction set, CISC, and it's not it's not like ARM or x86 that Windows is famous for using, but it's basically just a set of instructions that you use to do some computing. Actually, we can look at most of the instructions down here, most of the fundamental ones. So this is, it might look confusing, but if you keep looking at this page, if you keep looking at this diagram, you will see that it actually shows all the instructions. So it's a load store architecture. And what does load store architecture mean? Load store. Yeah, like many RISC designs, RISC-V is a load store architecture. We can go to that page and we can check it out. So it's a load store architecture. In computer engineering, a load store architecture is a register to register architecture. Is an instruction set that divides instructions into two categories. Basically, loading from registers. You pick something from some buffer somewhere that you're going to use. You use it, and you do some operation on it, and then you put it in another register. And once you start looking at it that way, you start understanding it very easily. So the fact that it's a load store architecture, and the fact that most of the so you're going to either work on something called an immediate, or you're going to work on some register data, or you're going to work on some or you're going to be given some operands. So you can either work on some operands, which is RS1 and RS2. Usually RS1 is usually the source, RS2 could be the second thing that you're given, or you could work on these things called immediates. And immediates are sort of like, think about them like constants. So they're sort of this bit of data that you have that you can use at any time. You see, and then you have these operation codes, and the operation codes tell you to whether to add, to subtract, to increment, to multiply, to shift left, shift right. So basically here I think I have something open here. So this is the same document that we are looking at from the other page. Let's look at it better even. I will remove this so that it's even more visible. Let me know if you want to see more. But basically, you have an opcode, and then there's a type of instruction. So there's an R type, an immediate type, a shift type or a store type, branching type, I don't remember what the U type is. I think it's under 0 or something, or unless 0, and then there's a jumping type. So control F, S type, S type, S type, type. So there's types of instructions. Yeah, partially specifically 6 types of instructions format. 6 types of instruction format. So there's somewhere here, you'll see them. RISC-V types of instructions. This is also, I'm not really teaching, I'm also, because I'm reviewing what I was doing last year. I'm trying to remember what I was doing last year. So I'm also trying to learn what I was doing last year. And you're just joining the journey with me. So there's types of instructions. So there's risk V types of instructions. Yeah, this is okay, but this is the full one. I don't want this one right now. Yeah, upper type. So this, let's go to here. This looks better. So there's all these types. If you look at the types, they start to make sense. So as shown in the later slides, the ISA has two sources, one destination operand. RS1 and RS2 are the source operands, and then the RD is the destination operand. And then it divides only, the format of the instructions are divided into only 6 types. So let's go find these types. So there's, I would like to, amazing. So we found them. These are the 6 types of instructions in RISC V. R type. This is a register operation. So this is you're basically instructions use only registers as source and destinations. You're not working on immediates. You're not working on constants. You're not you're picking something from a register, doing something to it, and putting it back into a register. So let's think about something like increment. You pick a number from a register, you increment it, and you put it into another register. You're not using any other thing outside of a register, basically. And then there's an immediate type. Immediate type instructions has one of 2 source operands, and then specified within the 32-bit instruction word as a 12-bit constant or immediate. This constant is regards as a 12-bit signed 2's complement number, which is always sign extended to form a 32-bit operand. So basically this has a constant. Let's say you're doing a for loop, and you have this increment plus 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 plus. Basically plus plus is plus 1. You can't go always fetch a 1 plus it to this, fetch a 1 plus it to this, fetch a 1 plus it to this. And later as we work on this CPU, you'll start realizing there's this nuances where we get to a thing called pipelining, where you start making the thing more efficient. And when you make it more efficient, you realize everything that I need to use. So if I make a program right now and I declare a list of constants, we can make all of them immediates. And then I never have to fetch a constant. I never have to, if anywhere in my program I need to use that constant, I can just use it as an immediate rather than go fetch it somewhere else or something of sort. Basically, that's what immediates are. They're constants. And you can use them rather, or if you have a pi, or if you have a square or something like that, there's things that are just defined already that you don't need to go and fetch. You will see as we advance into this journey, you will see there's a fetching and there's a loading, and once we start breaking this thing into a pipeline, there's fetching, there's loading, there's operating on the thing. So all of these are expensive operations, and once you want to reduce them as much as possible. And then there's S-type instructions that are exclusively used for storing contents of a register to data memory. So this is something where you either want to write to ROM, or you want to write to RAM, or you want to write to some other storage type of memory, not necessarily ROM. You would never write to ROM because it's read-only memory, and that's your program. You will never write into your program, but your program could write to RAM, and something could pick it up from RAM, another program, or your program itself, or your program could write to some like external type of memory. So that is an S-type instruction. And there's a B-type instruction, which is a branch. So if not equals 0, if greater than 1, if greater than 3, those are branch type instructions. So there's some instruction where it goes like either take the left side or the right side of this equation. Basically, that's a branch type of instruction. So that's how you do things like that's how you do Hello? I think I'm back. Hey Nathan, did I go on mute now? For the whole time? Okay, it's okay now. Was it okay before? Hi Nathan. Was it okay before, or was I mute all the way through? Oh, like a minute. Anyways, yeah. So I was having a sip of water, and since you've given yourself as the one who will talk, do you have any questions? Do you have any questions, Nathan? I should probably start putting this in this folder. Yeah. So let's actually do this and make a docs folder in the repo. Save. And do you have any questions, Nathan, so far, so that I can save this document and then we can move on. Where's this file? Where's this file? No, this is okay. We can put this in the readme. Let's put that in the readme of the thing so that cd okay, and tiny risk and vim, and let's add what is this? Yeah, let's do it. Yeah. Okay. Helpful links. So no one has any questions. We can keep going forward. Okay, so let's save that. That's fine. And then I also added some docs here, and I would like to put this file into I would like to put this file into that folder as well, so that we can actually always have that file. Where am I searching? How can I search? Squee card. Okay. I see. So there's this folder here. Oh no, man. Yes, documents are risk v implementation documents, copy, move to, and then let's say go documents. Let's go into eng, let's go into tiny CPU. And then I'm going to push this quickly, and then we can keep going. Docs, select. Why is that? Why didn't that work? Git status. LS docs. It's fine. We can just do it again. What do I need to do? Control save, and then save. Keep. Resume. What? Let's just link it then. Copy, yeah. Let us just link it then. The README. Okay, cool. So there's that. There's that. Git status. Git add everything. Git add readme docs. Not what we've done yet. Git commit dash n add which git commit dash n add docs. Docs git status. After this, we'll just do the thing. Git commit dash and git push. Okay, cool. So now let's actually jump into our code. So we have some code here. Okay. So we have some code here. We have some code here. We have the actual code here. Space A. No, this should not be commented out. Space A. Okay. And then what's going on? So we can jump in between in between both of them. So the other thing I needed to do first of all is you see here. You see, there's a mistake here. Oh, I might have fixed it. Okay, cool. Here. So this is initial begin. This is basically some instructions that we are using to test our CPU. We're just writing instructions up, and we're just testing that our ROM is actually working on them properly. However, as you can see here, this is a Verilog file. This is a .v file. This is a Verilog file. This is not a test bench file. There's no _tb on it. What means, and initial begin, I have come to discover, is not a synthesizable Verilog. It's initial begin Verilog. Initial begin is not a synthesizable Verilog. So which means this is just here for verification purposes. We can use it for testing, but it really can't belong to our actual synthesizable code. When you synthesize Verilog, you basically compile it into a network of transistors that works like a digital circuit. So And the Verilog initial block is just for using for testing. You can't really synthesize this. So let's actually look at that first. And actually, I would like to know, if possible, which branch? Okay, cool. I'm on the PR, so that's fine. So let's read that first. Let's read this first, and then we can go for. So a set of Verilog statements are usually executed sequentially in simulation. These statements are placed in a procedural block. There are mainly two types of procedural blocks in Verilog: initial and always. Initial single statement, initial begin, multiple statements. What is the initial block used for? An initial block is not synthesizable. We want to look at synthesizable, so we understand what synthesizable it means. So synthesizable means basically means compiling this into actual digital circuits. We'll get to that later. Let's not overload ourselves. So we can't use this is like an assert. You can't use in some languages you can use an assert in your actual code, but in this language it's basically not. It's a setup. It's like when you're stubbing tests and you mock something and then you use it and such. The initial block is not synthesizable and hence cannot be converted into a hardware schematic with digital elements. Hence, initial blocks do not serve much purpose than to be used in simulations. The blocks are primarily used to initialize variables and drive design ports with specific values. So basically, that's the story here. So we need to change that. This is an issue. We need to change that so that this is actually not here. This does not belong here. So this is, first of all, this is a typo. We're gonna have a lot of fixes after this. So let's actually go. What we can do is we can remove this and then we can go here and we can place this in our test block. And I would like to put it before the first initial begin. So here, and that here's the code. However, now ROM does not exist. So this ROM that we want to use, remember. So let's say that. Let's go back to our. There is a ROM here, as you can see here. Let's actually find the first one. A ROM is a memory 16 read-only memory 16 registers whose size is 8 bits. Actually, this is now whose size is 32 bits because this is a RISC-V32. Okay, cool. So this is 16 registers which we use for we pretend are ROM right now. So in a normal CPU, if you have a microcontroller, this would be your flash memory. So embedded flash or whatever. I could actually do. Let me do an example here so that you can see. So this is an FRDM MCX N236. So this the thing I'm holding on my hand is this microcontroller. So let me actually ask Nathan, does it make sense the way I'm jumping from MCU to FPGA showing this example? Should I do this or should I just keep on with the Verilog? Let me ask the audience. Shall I actually show, and while they decide, let me actually do it. So it's Zephyr project. Zephyr, it's fine. Source inactivate. West control R west build B FRDM MCX. Yeah. So let's make a blinky samples here. A Zephyr blinky samples. So let's make a sample here and we run it on this MCU. And that MCU here. That MCU is this thing. I'm teaching like people don't know what I'm doing. I'm assuming if you're watching this, you don't know what I'm doing. So I'm just gonna give you all the information. FRDM MCX. So this is this. It's uh, ARM Cortex M33 microcontroller. This is also a RISC style. This is also a RISC. It's not RISC-V. It's actually RISC-V, but it's not. It's a RISC CPU implementation. This ARM Cortex. So Cortex M33 is yeah. The ARM Cortex M is a group of 32-bit RISC ARM processors. So basically the same thing. This is the processor. We're making something like this processor. And what I wanted to show you is this thing has flash, 1 MB dual bank flash, chip flash. This is where you keep your program that you write. Okay. So in our code right now, what we are doing in here, we have 16 registers. This should basically read from somewhere else. It should read from some non-volatile memory. Whenever this thing is, whenever the CPU is built up properly, we can point it to a reset address. And I'm just realizing this now. We can point it to some address of some memory, and we can always tell it, start your program from here. So start running instructions from here. But for now, while we're testing it, we will have this 16 registers here. I think eventually this will disappear as our thing becomes more complicated and more feature complete. This will disappear, and we'll start actually using different modules here and there. So this is me just remembering what I was doing. So there we go. So here is this microcontroller, and I'm gonna run a program on it. I just built a Blinky program on it, and I'm gonna just do a West Flash. And as you can see, what will happen here is boom, I think it's already blinking. I'm pretty sure it's blinking. Yeah, there you go. So you can see a red light going on, off, on, off, on, off, on, off. And we can actually do pico com -b -q -b 115200 dev TTY SCM0. That's cool. And you'll see this the microcontroller will tell us when it is turning the LED on, turning it off, turning it on, turning it off, turning it. Basically, that's it. That's a program. So that program is basically this set of instructions, right? It's not the exact same thing, but in that CPU, it is following a set of instructions, which is the instructions that we've just moved to Control E, and that we've just moved to our test bench. So as you can see here, I have an add immediate, I have an add one, I have an add, I have an and immediate, I have an or immediate, I have an add immediate, I have add immediate, and then I have a store word, and I have a load. Oh, I see. I actually understand this. So basically, we store a word into some place, and we load a word from some place, and we this is what I was doing. Oh, okay, cool. Nathan, who's watching the stream, and I'll do it for him because he's watching the stream, wants me to step through the program that I am making. I believe I can do something like, it might be difficult, Nathan. Might not be that easy. CD project West source vn source vn activate. So I have to activate a virtual Python environment for Zephyr. This is just normal stuff, and then I think I have to do West attach, and that should work. Yeah, cool. So this is it's in GDB, and I think we can do something like reset. If I remember, oh man. How do I? let's see. I've forgotten. I always have to look up how to do West touch. Okay. Actually, no. If I'm correct, we can do Control C quit. Yeah. Yes. If I'm correct, we can do West debug, and that should actually, yeah. So it's not blinking right now. So this is now in it is now in debug mode. So I'm now walking through it normal GDB. So we can do a break main, and then we can do I think we can do right now, we can do something like a continue, which will go all the way to main and it will stop. Okay, and then see again. Okay, what if I do a next? What if I do a cc a quit, and I just like yes, and I say yeah, and I just West debug again. Let's see what happens. Okay, next. I only know how to debug our own our custom hardware in the West debug, and I don't know if this hardware has been set up for debugging already. That's the thing about Zephyr. When you're working on something, you need to know what's debug. No. GDB reset. I want to walk through this, but I have a device that I can walk through, but it has proprietary code, so I can't really show you that one. Will R work? Will R run? Yeah. What if I do that? No. Yeah, well, let's say yes, and then what happens? Okay. Next. Oh, okay. Okay. Yeah, let's look at that one. Okay, we can do restart. This is the problem with GDB West debug. Okay, so let's see, it loads the ROM start, which is actually the thing we were saying. So you see, it loads the where the ROM is going to start from, loads the actual text of the code, and then it loads some device area, some ARM some ARM specifics, some NXP specifics, some interrupt service routine table, GPIO driver, cloud control driver, UART driver, and then it so we can do that, and then we can say load, and then we can say continue. Yeah, So okay, cool. I know what to do now. Quit here. Yeah. So sorry, this I never like. I keep forgetting because it depends on what I've been doing for a while. So we want to do this, and then we want to do a load, and then we want to do a break main. Okay, so it's going to break at that, so it's basically there, and then we want to do a continue. Yes, so it's at main. It's at main there. This is now in main, and then I want to do a next. Yeah, so we're walking through the blinky control shifting and then Zephyr samples basic link. Okay, so here we go. Source main. I think we're on this line now. Is if GPIO is ready. So yeah, there you go. And then next one, we're gonna go into basically this is going to be. I think we can look at LED. We can say something like that. GDB variables. Variable debugging. So I want to see the variables. How do I just like pick one? How do I? PA. Okay. PA. Okay. PRET. Let's look at PRET. Optimized out. PLED. Optimized out. What other thing can we look at? PLED state. Where are we? PLED state. True. Okay, so it says LED state is true, and that's basically what were we looking at. I like my debug to be on the right side of my. And I'll leave this here. So I like my. Yeah, if I like my code, my debug to be here. Oh, this is odd. My code is here, my debug is here. Okay, cool, but I'm reading. Okay, cool. So Nathan, you can see. So we're looking at LED state. LED state is true now. But we are on here, we are on GPIO is ready, and we can look, I think we can look at ret, but let's step again. Ret equals GPIO configure and then I think we can actually look at pret. It should be 1 now. That's optimized now. So ret is sort of like I would call let I mean ret, yeah. When I'm speaking about ret, I'm talking about this integer here that we use. It's a return integer that we use all over the place. Basically, well, what it is, I think it's an immediate, so we can't really pull it out, so it gets optimized out. But here, let's see. So it's optimized out. We can't really look at it. This line number 32, we do a GPIO pin configure DT device tree, and we pick a device and we configure it as a GPIO output active. And then well, let's step on to the next one. And then the next one, if ret is equal 0. So here, look at what happened. If ret is equal 0, basically, the moment we configure the GPIO as active, the LED came on. And then if I step again, if ret is equal 0, so this is fine. It's gonna keep going now. It's going to toggle. Ret is equals toggle pin toggle DT. I think it's off now. Oh no, I need to step through this. Next. Should be off now. Yes, there you go. And then if I step next again, if return is equal to 0, let's say we need to change the LED state. LED state has been changed, so let's do p LED state. It's going to be false now. Okay, wait, just wait. N. So this is now, it's gonna print, but I want to p led state. So now it's the next line. It's actually changed. So cool. And then we can do a next again, and it's going to sleep for 100 milliseconds. So we can do a next here, and we have to wait a bit. Yeah, cool. Now it should be, but no. So now we need to toggle it again. It needs to toggle it again. So this is classic. Nice one, Nathan. So this is actually the kind of stuff we need to realize. So while one is a branch, and then km sleep here is a jump. So it sleeps for 100 milliseconds. It's defined, yeah. 1000 milliseconds. So 1 second. It sleeps for 1000 for 1 second, and then it checks if is one still one. Yes, it jumps back to here. Okay, so let's see. So it's still off. Okay, it's still off. So let's do a next. It should be on now. There you go. Nathan, questions? Anyone, questions? Before I go back. Any questions? Or say if everything is good, and if everything is good, we keep going. Can I go back to writing Verilog now? Sure. Whenever a question comes through, we will see. We will work through it. But I've realized there's a lag, so I'm kind of wasting time while I wait for any questions. Cool. Yeah, Nathan says cool. So we've walked through it. So the code actually works, and it'll keep going and keep going and keep going and keep going and keep going. And so we can do something like a continue here, I think. Yeah. And if we do a continue there, as you can see now, Nathan, it just keeps going. Keeps going, keeps going, keeps going. Yeah. Okay, perfect. So leave the MCU alone. We were not working on the MCU. We were actually working on thanks, Nathan, for forcing me to debug Zephyr Live, which has actually sometimes you guys make me do stuff, and then I realize it's so easy and I can just do it all the time. But I don't do it all the time. It's fine. Okay, cool. So we need to move this ROM over to the device that we're testing. So whenever you write a Verilog test bench, let's go back here. I've already been at this for an hour, so we might break soon, unless there's questions. So whenever we've initialized the initial blocks are for simulation, so it's fine. So let's actually look for test benches. Test bench. Verilog test bench. So what is a Verilog test bench? A Verilog test bench is a simulation environment used to verify the functionality and correctness of digital design described in the Verilog hardware description language. Cool. We know all of this already. The purpose of a test bench is to provide a way to simulate the behavior of design under various conditions, inputs, and scenarios before actually fabricating the physical hardware. It allows designers to catch bugs, validate functionality, optimize designs without the cost and the time associated with physical prototyping. So basically, simulation allows you to so first of all, they're talking about like fabricating physical hardware. This is like next level. This is ASIC stuff. And ASIC stuff is where an ASIC is ASIC is what is an ASIC? ASIC is like the next part. So this CPU on this board is an ASIC. Once you've written your soft CPU so well and you know it works very well and you've tested it and you know the speeds of it, you go and you get that converted into a physical design, a physical integrated circuit. And then you get something called a fab lab to make a physical, it's not just a software copy of this. And this is now what is in your Raspberry Pi, what is in your STM32, what is in your AMD. My processor is something like AMD GTX or whatever. I don't know what my computer is about. So this your processor, yeah, my processor, my computer is an AMD Ryzen 5 3600. So that is an ASIC. That is something that has been designed to do a job in a specific way. Okay, and it's been once you know which application that this digital's design, you're making a CPU, you're making a camera pipeline, you're making a RAM module, you're making a sensor of some sort. When you understand how you can use these designs really well, you can make anything. You can make a sensor, you can make a display, you can make a camera, you can make an image sensor, you can make a temperature sensor, whatever. It's how you arrange the little wires and transistors in the circuit, and then you can use them as you deem fit. Okay, cool. So basically what they're talking about here is when you make ASICs, when it becomes when they say fabricating the physical hardware, this is that point. But you can still simulate. So okay, there's a difference between something called an MCU, a microcontroller unit, a CPU, which is the same as a microcontroller unit, and FPGA, and an ASIC. ASIC is basically both of them. ASIC is an FPGA and a microcontroller, if you think about it. An ASIC is a very expensive thing. Like the first ASIC you make, then the ASIC number one is going to cost you like millions of dollars to make that one, because of the development, because of the design, because of the fabrication, because of the testing and all of that. It costs a lot. But once you make one, it costs almost nothing to make copies of it. It's like photocopies of it are very easy to make. You can make millions of them very cheap. But making one is very expensive. And then an MCU is basically a computer that you can get that you can use for anything, kind of. You can use it for whatever you want to use it for. It's a general purpose computer. You can use it for gaming, you can use it for streaming video, you can use it for making a phone, you can use it for making a digital screen. Whatever you want to use your computer for, you can use it for. And then an FPGA is a blank logic canvas, basically. You use an FPGA when you have a lot of parallel data, and then when you need some weird assortment of peripherals. So say something, you need something that, I have a friend on Twitter, and he's doing, there's nothing you'll see, I don't hide that much. I have a friend on Twitter, and he makes robots. Ru, where's Ru? Ru. So Ru makes robots, and the most recent robot Ru is making needs 24 ADC channels. Here you go. I need it modified to 24 ADC channels. Now, to build a 24 channel ADC streamer. So if we go and look at, say, the FRDM SNX, this one, the one that we were just looking at, it has ADC, but let's see how many channels it has. It will have something like 12 or 8 or 6 like that, or something like that. ADC. Yeah. So it has, look at that. It has one on board and one on chip. Yeah, okay. One enabled and one disabled ADC. So two. Okay. And you can look at something like, say, let's use this. Let's pick some sort of STM32N6. I like this one because this is the one I like playing on. Nuclear N6. That's nuclear N6. Let's look at that one. How many ADCs does that have? So let's look at ADC. It has a one ADC, a one enabled and one disabled. I have I'm just looking around and seeing what controllers I have. Let me look. I have an NXP IMX RT1060. Yeah, I have an RT1060. Although that is an XP twice. We'll look at RT1060. Let's look at that one. That's probably, how many ADCs does that have? ADC, you see, it has one ADC, one enabled, one disabled. Let's look at RP2350. I have that one. I have one of those. Oh, I have quite a lot of NRFs in front of me. RP2350. Let's look at this one, and you can see it also has, I mean, it only has one ADC. All the other ones have two. And then I have this is an NRF 54L15. So let's look at NRF 54L15. NRF 54L15. Yeah, let's look at that one. DK, I have that one. So let's see that one. How many ADCs does it have? One ADC, even a really nice one like that one. I have NRF 91. NRF 91. This is an NRF 91. This is actually quite a beefy one. It's quite a beefy 9160. This one, I think this one. And how many ADCs does it have? This one doesn't even have, it's not even listed stuff yet because it's not even complete yet. Doesn't even look like it has ADC. So look at that. What am I saying here? When you need custom things, when you need something with a lot of something, you're making a sonar sensor, you're making a sonar system, and you need 15 microphones. Most microcontrollers will not have that. You're making smart glasses and you need 16 cameras or 5 cameras. Most MCUs will not have that. And remember, you're still making a portable device, so it's a low power device. So you end up in this place where you need many microcontrollers, or you need something that you can actually build peripherals that you want. You want 15 UARTs or something. So you get an FPGA, and then you make all of these hardware blocks that you need, and you use them. And by the way, you don't have to make all the hardware blocks that you need. There's something called open cores. It's something called open cores. So there's actually open source hardware that is already, it's called gateware because it's FPGA, and this, it looks like this, but this is very advanced. They work on hardware, so they don't really care about this website, or they do, but it works. And yeah, so what I'm saying is they provide hardware cores or IP cores that you can use. So you take an FPGA and you add 24 ADCs on it. I'm sure there's going to be can we find an ADC? Can we find an ADC? Can we find an ADC? ADC. Can we find ADC cores? SPI master, I2S to ADC peripheral, ADC core. Can we find something like that? SPI master receiver, parallel to that, SPC flags. I2S is ADC, or maybe ADC is too low. But basically what I'm saying is, you take one of this, we can look at one of this, so it's fine. We can look at one of this. It's fine. You can, yeah. Design done. Stable. Basically, browse. I think we can look at that. Let's go to SVN for ADC, and basically there's a lot of cores that you can use. So here, yeah. So let's go and look at it. I just want to look at branches, perhaps. I just want to look at this is the old GitHub. But what I'm saying is all of this, you can get a CPU, you can get so you can get something like vex risk. This is a CPU. This is a CPU. This is a CPU that this is a CPU that is done in Verilog. You can get something like Litex. Litex is also a CPU that is done, and it also has a lot of other cores. But Litex is actually Litex is not a CPU. Litex is a system on chip. So a system on chip is something like the RP. Yeah. This is a system on chip. So it has a CPU on it. It has UARTs. It has memory. It has RAM. It has all of these things that you put together, and then you call it a system that you can use, that you can give to someone and they can use. Not that they have to build up stuff on. But also, the market is surprisingly popular on doing that. Anyways, I've gone on for too long. It's already been an hour, and I didn't even do what I came here to do. I was just explaining what I'm trying to explain, what I'm trying to do, trying to connect. So let's do the last part of the code, and then we can leave that for today, and we can commit it in. So this ROM that we've segued into microcontrollers and come back from, it's here for when we're testing. Whenever we have a test bench, you instantiate the module that you're testing, and you usually call it a device under test if it's the top module, and then you can always call it something else. You can call it RAM under test, but DUT means device under test. So this is the copy of this module that we're going to be using for testing. So I'm running short on time, so what I'm going to do here is I'm going to add DUT dot DUT dot. I could have used macros. I could have used some vim. Yeah, I cannot actually do that. No. Why? Okay. Why is this not? Can't I do that? Yeah. Okay, actually, let's look. I can't actually do that quite easily. So this is 7. I can go 7j dot dot. I can't say dot 7j. Can't I do that? Anyways, I wanted to repeat the command for the next 7, and it's anyways, it didn't work out. So, but this is fine for now. This is fine for now. So what we're doing here is we're making so that the ROM lives in the test bench, because when we actually leave it in our code itself, our code is not synthesizable to be able to run on hardware. When is tomorrow? Friday. I can do another stream tomorrow evening when we work on this. So it seems like I'm really excited to keep working on this, and we can stop there today. So let's just make sure everything built. your test. I just want to make sure everything builds and it runs. Yeah, so let the tests that are failing fail. What we're going to come to do tomorrow is we're going to come and go through this code, and we're going to make sure that this R-type instruction is actually an R-type instruction. We're going to make sure that this I-type instruction is actually an I-type instruction, and this L-type instruction is actually L-types, and this S-type is an S-type. So just so that we can walk through all of these results, because I noticed some discrepancies in my code here, and I would like to just make sure that they are properly done. And first of all, we'll do that, and then we'll add some code to make sure it does well. We will change the tests and we'll change the code, and we'll keep on going so that eventually we have like this very fleshed out processor that we can work on. Does anyone have any questions while we commit this? Does anyone have any questions or requests while we commit this? Remember, by the way, we have a community that is down in the description. You can join our community and you can talk to us and you can work with us and you can ask all the questions while you're working on your CPU and everything, and you can, come discuss what you're working on, and we have we have an active place for people to work together, and we can always, work together. So, okay, git push. This is already pushed up. You can check the PR. It's online. This is this should be the pull request. The pull request is here. There's an open pull request. We can go for that, and then we're gonna stop there today. It's been an hour of sharing this work. I'm really glad we did it, and I'm thankful for everyone that showed up. Thank you for coming today. See you guys tomorrow. I don't know what I'll be working on, but I will try and keep this going from now on so that we can just get all of these things going. And by the way, if you're going to be at Embedded World, I will most likely be there in Germany. Let's meet up. Let's do some stuff if you wanna meet up and talk. Cheers. Thank you so much for showing up today. See you tomorrow when we work on other things. And thanks, Nathan, for letting me know that I was on mute. And yeah, thank you so much. I want to just... Oh, okay, cool. It shows up here. Okay, cool. Thank you so much. Cheers, everyone. And that was a lovely stream. Amazing.